So we're going to finish up the notes for chapter 4, and this particular section is one that we are going to use again and again and again, both in chemistry and also in your future work. So I want to make sure you understand this. You have a pretty good foundation on this unit. So the unit is called molarity, and as you can see, its symbol is a capital M. So you've seen this all along in lab. For example, when you use 3 molar, that's how we read this, again, as molar. Sulfuric acid. The 3M is an important concentration unit. If there was also a 15M on your chemical tray, you would not want to use those interchangeably. They have very different concentrations, which means different rates of reactions. So if you use like 15 molar H2SO4 when you needed 3 molar, it's probably going to generate an excessive amount of heat and can even crack your flask that you're using. So we got to be careful to use the right concentration of things. In addition to that aspect, as it turns out, molarity is an excellent conversion factor. So you want to train your brain to recognize the capital M and immediately translate that into 3 moles of whatever substance you have for every 1 liter of solution. So the substance being dissolved is always called the solute. And on the bottom, we have the entire solution, right? And so we don't always define these when we're thinking about what molarity means, but at least as it applies to your lab, it is helpful to do that. Because there's a difference between just the moles of acid versus the liters of the solution, right? The liters of solution include the acid and the water. Okay, so that's what the denominator is about. Right? And so this is actually a conversion factor that can be used to, if I have a volume, I can cancel liters and get it into moles. And then of course, once we're in moles, we can do everything we know how to do with that, like turn it into grams or turn it into number of molecules if you use Avogadro's number. Avogadro's number. There we go. There's nothing to do with autos. Okay. This is similar to the way in which we use density. So I just want to do a quick example, right? If I had 5 milliliters of gold, and I know that the density of gold is 19.3 grams per milliliter, we can quite easily figure out how many grams of gold are there, which is what pawn shops and so forth are actually going to pay you based on. And when they measure the density, if it's not 19.3, they'll know it's not pure gold, right? So in this case, you get 96.5 grams. And so we set this up using dimensional analysis, just like all of the conversions do. And molarity is going to be very, very similar to that, right? So if I had 3 moles per liter, and I have 1 liter of solution, then that means I have 3 moles of solution, or sorry, 3 moles of solute, which is H2SO4 in this particular example, okay? Of course, because molarity is a conversion factor, I can also flip it over. If I know the number of moles that I have or the number of moles that I need, I could also solve for the volume just by inverting a ratio here, just like we do with density. All right, so let's do some practice problems. It's a good idea for you to pause the video and try these on your own, okay? So first things first, I see 0.500 molar, so I'm going to convert that into moles of NaCl per 1 liter. Now, I did want to mention here, the abbreviation for moles is MOL, not little m, because that actually has 2 other meanings besides what we talked about in class the other day, so liters. So we don't want to abbreviate moles too much. You should always include a unit and a chemical with every concentration. And so the question asks, how many moles are in 75 milliliters? Okay, well, so if we're starting at 75 milliliters, we can multiply by the molarity, but milliliters and liters are not the same, so I will also need to convert from liters into milliliters. Okay, So in this case, we have liters canceling here and milliliters that cancel here. So the only thing remaining is moles. Now it's worth noting, I don't care what order that you do these conversions in. Maybe you want to do milliliters to liters first and then cancel your liters and get to moles. That's fine too. But you do need to show each one of these steps, okay? It's important in being able to troubleshoot your answers and things that you are clearly outlining what you're doing, particularly critical in the lab. Right? So that's our answer. We get 0.0375 moles, right? Now, going back and looking at our sig figs, which is always the last step in a calculation, you have 3 in the molarity. I kept all those zeros on purpose because these zeros are significant. But we only have 2 in our final volume here, so we're going to have to round to 2 sig figs because we are doing multiplication. Okay. Perfect. All right, so now we have a different kind of problem. So this problem here is going from a volume into the number of moles. And the way you do that is using molarity. Okay. In this problem, we're starting with grams. And it looks like we're dissolving it. Okay. So in order to plug it into the formula for molarity, we need to get grams into moles. We do that the same way we were practicing in the last couple videos. We're going to use the molar mass. I want to caution you that you should be calculating the molar mass on your own and not using Google. So far, I've seen a number of people relying on Google getting the incorrect numbers, which whoops, the answer is 50. I just know this one. I didn't Google it. I use it a lot. So I was saying you want to be careful because sometimes you get the wrong compound or they round too soon or whatever. Remember, 2 decimal places is good. It will ensure that you're not losing significant digits. And you also need to remember the unit from the periodic table is always grams per mole. So this is an important thing for you to actually be calculating on your own. Can Google do it for you? Sure. Can it do it for you on your final? No. And it will be on the final. All right, so now we have our molecular weight. I flip it over because I want to cancel grams, which is what we're starting with, right? And so this will tell us how many moles we have, which is 0.085557837. I only have 1 sig fig. I am not going to round that soon in the problem. I always keep at least a couple of extras. So I'll just write 856. But I know I only actually get 1 sig fig here. Okay. Then it wants us to convert. So we're trying to get to molarity. So in order to get there, we have to convert 500 milliliters into liters. Give ourselves a little more room for that. So 500 milliliters. Again, dimensional analysis is your friend here. It will make sure that you're not multiplying by 1,000 when you should be dividing. All right, as long as you know there's 1,000 milli in the base unit, you'll be okay. Oh, these zeros are not significant, so I actually am not going to keep them. That would be misrepresenting how carefully this measurement was made. So it's going to just be 0.5 liters. And so to find the molarity, we'll just take the number of moles and divide by the number of liters. And that's our molarity. We get 0.171115674. So I know I only have 1 significant figure. I did not measure this number very carefully at all. So I have to round that to 0.2 molar. Okay, so that's our answer on that one. All right, so this goes the other way. So this problem was calculating the molarity from mass, all right, which took some conversions that we knew already, and then you just plug them into the formula for molarity, right? Here we're going to kind of go a different direction. We're going to start with a molarity, which again, I'm going to translate that immediately. So it's moles on top and liter on the bottom. I need 1.5 times 10 to the 5 moles of NaCl. That's a lot. All right, so we're going to start with that number. And I notice that because I have converted this big M into moles per liter, I notice that there is a common unit here. So I'm still doing dimensional analysis, but this time I have to put moles on the bottom because that's what I'm trying to cancel. Oh, and it asks how many milliliters. I'm going to go ahead and stack in that conversion as well. I need 1,000 milliliters for every 1 liter. So that'll cancel liters. Moles gets canceled, and we're just left with milliliters. You should practice entering scientific notation correctly in your calculator. So this number would be like 1.5 EE or EXP, or sometimes the cheaper calculators say 10 with a little caret and arrow over the top. But you need to, search up your manual and figure out how you actually enter scientific notation. It's not just multiply button, okay? So anyways, because like here, what it would do if you did just the multiplication button is it probably would take just the 10 to the 5 and divide that by 0.5 and not account for the 1.5 unless you use a bunch of parentheses. So what I typed into my Casio little calculator here is I type 1.5 EXP, that button. Okay, again, that'll vary from model to model. You can figure it out by looking for your manual, searching for scientific notation. So I put that in there, and then I'm going to divide by 0.5. And we end up getting a very large number of 300,000. But then I also need to multiply that by 1,000, in which case we get a big number, which we knew because this was a lot of moles to begin with. So 300 million moles, or milliliters. You could write this in scientific notation, so that would be fine. We technically have 2 sig figs because there's 2 here, so really I should write 3.0. So the reason scientific notation is handy here is because in standard notation, you can't indicate which zeros are significant and which ones are not. There's no way to do that. But if you write this in scientific notation, you can. You can write 3.0 times 10 to the 6, 7, 8 milliliters. Right? So this is the best way to represent that answer. Let me draw to my screen. This is the best way to represent your answer. So we can use molarity in both directions, just like density.